As you read the first question, you ask yourself, are we dealing with mean or proportion? If we're dealing with mean, is it one sample or two samples? If it's two samples, are they dependent or independent? If we're dealing with proportions, is it one sample or two samples? And if it's two samples, are they dependent or independent? The first thing you want to do, if there's an appendix, check if you have histograms or box plot. Those are indication that you're dealing with mean. They will never give you a box plot in a question of proportion. In the descriptive statistics, we have things like the mean, we have the standard deviation. Also, if you scroll down, there is a box plot. So this is definitely a question about mean. Now, how many samples? With only one box plot, we have one sample. And if you look at here, one sample. We don't have to worry about whether we're dealing with dependent or independent samples because we only have one. Okay, perfect. Now let's go back to the question. Part A. Test the hypothesis that the mean concentration is less than 22. And we're using the p-value approach. So we have HO. The mean is 22. And HA, the mean is less than 22. So this test is one-sided. Now, in step 2, we need to compute t-stat, x bar minus mu 0 over the standard error of x bar. Right? SE of x bar is S divided by square root of n. X bar is 19.655. N is 22 and the sample standard deviation S is 4.507. 19.655 minus mu 0, which is 22, over the sample standard deviation 4.507 divided by the square root of n, negative 2.4404. Now, in step 3, we find the p-value, the probability that t is greater than the absolute value of t-stat, right? T-stat is negative 2.4404. The absolute value is 2.4404. 2.44. And this is your p-value. Well, let's go to the t-table. And we look for 21 degree of freedom, right? df is n minus 1. But n is 22, so 22 minus 1 is 21. We search for 2.44. 2.44 is between 2.07 and 2.51. So the p-value is between 0.025 and 0.01. This is 2.07, 2.51. The probability for 2.07 is 0.025 and the probability for 2.51 is 0.01. So p-value is between 0.025 and 0.01. Because this is a one-side test, we don't have to multiply the p-value by 2. We should actually multiply this by 1 because it's one side. And if it was two-sided, like if mu was not equal to 22, we would have multiplied the p-value by 2. But it's not. Now in step 4, we reach the conclusion. We compare the p-value to alpha, the significance level, which is 5% or 0.05. Right? Is the p-value smaller or greater than alpha? Well, any number between 0.025 and 0.01 is smaller than 0.05, right? Any number in this range is smaller than 0.05, so the p-value is smaller than alpha, so p-value less than alpha, and when the p-value is less than alpha, you always reject H0, which means you accept H1 or HA. There's strong evidence that the population mean is less than 22. The appropriate confidence interval corresponding to this hypothesis test is the following: negative infinity to x bar plus t crit times the standard error of x bar. And this is an upper bound the standard error 4.507 over square root of 22, 0.9609, and t crit from the t table 21 degrees of freedom at alpha equals 0.05, (1.72), (19.655) plus 1.72 times 0.9609, and this is 21.31. The upper bound for the confidence interval is 21.31, so the confidence interval goes from negative infinity to 21.31. Under H0, the population mean should be 22, right? And 22 is not in the confidence interval. Because 22 is not in the confidence interval, we should reject H0 and accept H1. And that's exactly the same conclusion that we had with the p-value approach. We reject HO. A test on the median is a non-parametric test, right? With one sample, we will use Wilcoxon sign rank test. The median is 22. The median is not 22, is different, right? Not equal 22. Now, the p-value right here, 0.022, and that p-value is less than alpha, which is 0.05. We must reject HO. D. The population must be normally distributed. The normal distribution. The data should be normally distributed in the population. If you look at the box plot, it's kind of skewed, right? Seems to be skewed to the right. So this is hardly a normal distribution. We may conclude that the population is not normally distributed, and as such, one must use a non-parametric test, the Wilcoxon sign rank test, as opposed to the parametric t-test. Now we're looking at question 2. Again, as you read the question, you look for keywords to decide whether you're dealing with mean or proportion. And I highly recommend that you check the appendix first. Is there any appendix for question 2? Apparently not, otherwise the question would have mentioned it. Remember question 1? We did have an appendix for question 1. Let's read the question and look for keywords. Okay? A researcher is interested in knowing the effectiveness of teaching English to non-English speaking students. using a computer-assisted program or a traditional. She randomly selected 300 students and assigned 125 of them to the computer program, 175 to regular classroom sessions. After 6 months, the 300 are given an examination. And here's the table. You have computer-assisted classroom sessions, and notice we don't have any information regarding the mean and the standard deviation. That could be a clue, an indication that we're probably dealing with proportion. If the question is about mean, I promise you, they will give you at least something like the average, the mean, and the variance, the standard deviation. Does the computer program increase the proportion of students passing the examination? Use alpha equal 0.05 and the critical value approach. We are told to use the critical value approach. We will not use the p-value approach as we did in question 1. So now we know the question is about proportion. Is it 2 samples or 1 sample? Right? Is it 1 proportion or 2 proportions? Because the formula is going to be different depending on whether we're dealing with 1 sample or 1 proportion or 2 samples or 2 proportion. We're dealing with 2 proportions or 2 samples. Why? Look at the table. We have 2 groups. We have 2 samples. We have the sample of the students that were provided the computer-assisted program, and the sample size for that group is 125. And you have another group, another sample of students to whom the traditional setting was provided. And what's the sample size for that group? 175. And so this is a question about proportions with 2 samples. Oh, one more thing. Are these dependent or independent samples? Well, clearly these are independent samples. One group of students was using the computer program and the other group was using the traditional classroom setting. These are not the same students, folks. Completely different people. So independent samples. Now we have everything we need to tackle the question. We want to know if the computer program increase the proportion of students. Keyword for stating the alternative hypothesis. Increase. We're going to use a one-side test. 1 percentage or 1 proportion is going to be greater than the other proportion. Let's first define the proportions. What is P1 and P2? P1 is the population proportion of students using the computer program, and P2 is the population proportion of students using the traditional setting. Okay. Let's state HO and H1. We want to know if the computer program increase the proportion of students. In H1, P1 is greater than P2. Right? Greater means increase, bigger, more. Under HO, the 2 proportions are equal. And this can also be written as HO. You move P2 on the left hand side, so P1 minus P2 equals 0. And under H1, P1 minus P2 is greater than 0. Okay? And this is a one-side test to the right. Right? Because it's bigger than 0. It's greater than 0. So it's one side to the right. And in step 2, let's find Z stat. and some people call it Z-calc or Z-calc. Now Z is P1 hat minus P2 hat minus P0 over the standard error of P1 hat minus P2 hat. Okay, this is Z stat. P1 hat minus P2 hat minus P0 divided by the standard error of P1 hat minus P2 hat. We need to find P1 hat, we need to find P2 hat, we need to know what P0 is, and we need to find the standard error of the difference between P1 hat and P2 hat. The P1 hat is x1 divided by n1, and P2 hat is x2 divided by n2. x1 is 94 and n1 is 125. Now if you ask, why is x1 94? Why not 31? Let's read the question. Does the computer program increase the proportion of students passing the exam? See, 94 students in the first group, in the first sample, pass the exam. So you use 94 as your x1. If the question was about failing, we would have used 31. Okay? N1, the sample size, is 125. And by the same token, x2 is 113 for the second group. N2 is 125. And 113 divided by 175. 0.752. 0.646. Okay, so what about P0? This is P0. P0 equals 0. It's the difference between P1 and P2. Right? This is 0. And what's the standard error? Now, in order to find the standard error, we need to find a pooled proportion. And the pooled proportion, let's call it P. And P pooled is x1 plus x2 over n1 plus n2. x1 plus x2 over n1 plus n2. And this is 94 plus 113 divided by 125 plus 175, and this is 0.69. So the pooled proportion is 0.69. We have P1 hat, which is 0.75. We have P2 hat, which is 0.64 or 65. We have P0, which is 0, the difference between P1 and P2, which can be found from HO. And you have P pooled, which is 0.69. Now, who cares about P pooled? Well, the standard error does. We need the P pooled to compute the standard error. So the formula is P pooled times Q pooled. Q is 1 minus P, bracket 1 over N1 plus 1 over N2. Okay, Q equal 1 minus P. So if P is 0.69, Q is 1 minus 0.69, and that's 0.31. So the standard error is 0.69 times 0.31 bracket 1 over N1 is 125 plus N2 175. That's your standard error. And so we get S equals 0.0542. Okay? And so Z stat equal P1 hat, which is 0.752 minus P2 hat 0.646 minus 0, this whole thing divided by 0.0542. 0.0542 is 1.96. We found Z-stat. Okay, use the critical value approach to decide whether the computer program increased the proportion of students passing the exam. So we need to compute Z-crit, right? We have Z-stat or Z-calc, and we don't have to compute Z-crit. We just have to find it. This is step 3. Z-crit or Z-table. We're using alpha equals 0.05. Because this is a one-side test, we will not divide alpha by 2. And because the test is to the right, the Z-crit should be positive. It's a right-sided test. It should be positive. If it was less, it would be negative. Okay? And from the table, you get plus 1.645. Again, it's plus because in H1, we have greater, right? If it was less, it would be minus. So now we have Z-crit and we have Z-stat. How do we decide if we should reject H2 or not? So the critical value is 1.645, right? And any value of Z-stat that falls above 1.645, right? Anything here will lead to the rejection of HO. But if you get anything below 1.645, below the critical value, the table value, you do not reject HO. So the critical value is a threshold, right? It's a threshold, it's a limit. And anything above, you reject. Anything below, you do not reject. But then you ask, why do we reject when it's above? Why not below? But then we have to go back to H1, right? Look at H1. It says bigger, greater, one side to the right. Like when the value of Z-stat is greater, more, above, right? The critical value, we do reject HO. Okay? So here you have 1.645 and you have 1.96. We are in the rejection region, right? You reject HO here. Conclusion, so we reject the confidence interval for the difference of the two proportions. If you look at H1, it's P1 minus P2 greater than 0, and that one side confidence interval, it's going to be a lower bound to infinity, right? Because of this. And this is a lower bound. And that lower bound is P1 hat minus P2 hat minus, right? It has to be a minus, Z crit or Z table times the standard error. But this is a different standard error. The formula for the standard error used to compute a confidence interval for the difference of two proportion is P1 hat Q1 hat over N1 plus P2 hat Q2 hat over N2. P1 hat is 0.752, P2 hat is 0.646, 1 minus 0.752 over 125 plus okay, this is 0.053 So the lower bound is 0.752 minus 0.646. How much is Z crit? Z crit is 1.645, right? So minus 1.645 times the standard error, which is 0.053. 0.053. Okay, how much is this? So 0.0188. So the confidence interval is 0.0188 to infinity. And this is the lower bound for that confidence interval. Based on the confidence interval, we can still reject HO because P0, right, the difference between P1 and P2, is not in the confidence interval. Right? This is not in confidence interval. If the value P0 was in the confidence interval, we would not have rejected HO. But because the value P0 is not in the confidence interval, we must reject HO, which is really good because that's the same conclusion that we had in the previous question. This question is clearly about proportion. It says an extensive national survey of students reported that 44% engage in such behavior, being drinking. Thinking that the proportion at its university was even higher, right? Proportion. Higher, keyword. A fraternity conducted a random survey of 500 students among 45,000 students at its university and found that 240 engage in being drinking. Are we dealing with mean or proportion? Most likely proportion, because we don't even have the average. We don't have the mean, which is the average. We don't have the standard deviation. At the 5% level of significance, test whether the percentage, the proportion, percentage, proportion, same thing, of students engaging in being drinking at the university is greater, more, bigger, greater. This is for the alternative hypothesis. Okay, so we know it's about proportion. Is it one sample or two samples? We don't have any indication that we're dealing with two samples, right? We don't have two groups. It's one sample from the population of students of the college campus. Do we need to worry about whether the samples are dependent or independent? No, because we only have one sample. Okay, so let P equal the population, proportion or percentage of students on that college campus that engage in being drinking. That's the population proportion. The null hypothesis HO and the alternative H1, the national survey reported that 44% engage in such behavior. That's the percentage at the national level. It's a population proportion. And since we're testing whether the percentage of students is greater, P is bigger than 44%, which is 0.44, against the null hypothesis that P equals 0.44. We're testing HO, P equals 0.44 against H1, P is bigger than 0.44. Okay? And this is a one-side test to the right. So that's step 1. And step 2, let's compute Z-stat. And the formula for Z-stat is P hat minus P0, the standard deviation of P hat, right? Not the standard error. And that's because the difference between the standard error for a proportion, for one proportion, and the standard deviation is that the standard error is P hat Q hat over N, but the standard deviation is P0 Q0 over N. and P0 is 0.44 in this question. Now what's P hat? Well, P hat is X over N. That's the sample size, 500, N equal 500. And we found 240 engaged in this kind of drinking. 240, that's X. 500, that's N. What about 45,000? This is the population size. We won't be using this in the calculation. Notice the population is very large compared to the sample. We will ignore the population size in the calculation. So we have 240 divided by 500. So this is 240 divided by 500. And that's 0.48. So P hat is 0.48, but P0 is 0.44. So we have P0 equal 0.44. We have P hat equal 0.48. The standard deviation of P hat which is root of P0, 0.44, times Q0, 1 minus 0.44, that's 0.56, divided by N, 500. And so Z stat is P hat 0.48 minus 0.44 divided by 0.0222, 1.802. Z stat is 1.802. Now Z crit, we won't divide alpha by 2. That's because H1 is one side, right? H1 is one side. From the Z table we find Z crit to be 1.645 and it's positive. This is a right-sided test, and as such the critical value must be positive. So we have Z crit 1.645. We will reject HO if Z stat is above 1.645, right? Above. But if Z stat is below 1.645, if it's less, we do not reject HO. We found Z stat to be 1.802. 1.802. This is Z stat. So since Z stat is bigger than Z crit, we reject HO. For the test above, find a 95% confidence interval to estimate the proportion of bingo drinkers at the university. And so this confidence interval depends on H1, right? So the confidence interval is also right-sided, right? It's going to go from a lower bound to infinity, or probably 1 because we're dealing with proportion, right? This is one proportion, so the upper bound is 1, but I guess you can also write infinity. I don't think the prof will mind. But the lower bound, that's the most important. This is P hat minus Z crit times the standard error of P hat. I am using the standard error to compute a proportion confidence interval, but I use the standard deviation of P hat to compute Z stat. Not the same thing. P hat is 0.48 minus 1.645 times square root of 0.48 times Q hat, 1 minus P hat, 0.52 divided by N. N is 500. Okay, that's LB. So the lower bound is at 0.44. So the confidence interval for the population proportion is 0.444 to 1 or to infinity. This is 0.444. The margin of error is plus minus 3%. What sample size would be required to be 95% confident in the estimate? Margin of error is 3%, which is plus minus 0.03. Confidence level is 95%, which means alpha is 1 minus 0.95. That is, alpha is 0.05. But then you have to divide alpha by 2. That's 0.025. And you look at the Z table for 0.025. You will find 1.96. Right? So the sample size N is P hat times Q hat times Z divided by the margin of error squared. 0.48 times 0.52 times 1.96 divided by 0.03. Notice I'm not even caring about the signs. It doesn't matter because you have to square the whole thing. So 1066. Now question 4. This question seems to be dealing with mean. If you look at Appendix B, we have 1, 2, 3 box plots. And I mentioned earlier that you wouldn't be provided with a box plot in a question dealing with proportion. And by the way, it says here 2 sample t-test. Right? T-test is for mean, not for proportion. Now, why do we have 1, 2, 3 box plots? We have 2 samples, right? We have a sample for energy and another sample for financial. This is about stock market, and those box plots are measuring the risk level of different stocks. So, energy stocks and financial stocks. So we're dealing with 2 independent samples. There's no reason to think that an energy stock is somehow dependent or related or paired with a financial stock. The problem statement doesn't give us any hint to think so. Let's look at the assumptions for using a parametric test. Parametric tests are t-test, z-test. Now, any test that assumes that the data should be normally distributed should have a normal distribution. If the samples are large meaning more than 30, then we don't need the data to have a normal distribution. We don't need that condition, that assumption. But the box plot should not be extremely skewed. Should be relatively symmetric. Okay. So let's look at the box plots and see if they are not extremely skewed and if we don't have many outliers. The third box plot, which is the difference between the energy box plot and the financial box plot, or the difference between those 2 data sets, that box plot is not relevant because we are not dealing with paired or dependent samples. We are dealing with independent samples. The energy box plot doesn't seem to be extremely skewed. It looks skewed, but not that much. Same for the financial box plot. And we have 1 outlier in the energy data, but that's just 1 outlier. And if you look at the samples, we have 33 observations for the energy sample and 33 observations for the financial. So those are large samples. And because they are large samples, we don't need the normal distribution assumption. We only need the distributions given by the box plots to be not extremely skewed with very, very, very few outliers, which is the case here. Okay? Now, let mu1 be the population average or mean for the energy stock. and mu2 the population average for the financial stock, right? We're testing HO against H1 or HA. Volatility of energy stocks is higher means more, bigger, than that of financial stocks on average by more than 0.25. So we want to know if mu1 is more than mu2 by 0.25. And of course, under HO, mu1 equal mu2 plus 0.25. And this can also be written as HO against H1, and under HO, mu1 minus mu2 equal 0.25. You move mu2 to the left hand side, and H1, mu1 minus mu2 is bigger than 0.25. So this is step 1. In step 2, let's find T-stat. X1 bar minus X2 bar minus mu0 over the standard error for X1 bar minus X2 bar. Of course, mu0 is 0.25, right? It's the difference between mu1 and mu2. So this is mu0. The right hand side of the equation in HO. Mu1 minus mu2 equal mu0. What is the standard error? S pooled times square root of 1 over n1 plus 1 over n2. S pooled is n1 minus 1 s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 2. Square root 33 minus 1, the sample variance for energy, which is 0.412 plus 33 minus 1 33 plus 33 minus 2, and this is 0.369. That's the pooled standard deviation. With S pooled, we can find the standard error, SE, 0.369 times the square root of 1 over n1 plus 1 over n2. SE 0.09. And so T-stat is the sample mean for energy that x1 bar minus x2 bar minus mu0, which is 0.25, and this whole thing divided by the standard error, which is 0.09, 1.955. Let's find T-crit and compare T-stat to T-crit to decide whether we should reject HO. Now we're using alpha equal 5%, which is 0.05. How many degrees of freedom? The number of degrees of freedom in this case is n1 plus n2 minus 2, which is 33 plus 33 minus 2. And so you look at the T table, you have 64 degrees of freedom You have alpha equals 0.05, and we find secret to be 1.67. And we found T-stat to be 1.955. Oh, by the way, we didn't divide alpha by 2 because we are performing a one-side test. We're doing a one-side test to the right, and so we do not divide alpha by 2. The critical value is 1.67, and of course we reject HO if T-stat is above 1.67. Right, so reject HO, and if the value of T-stat is below 1.67, we do not reject HO. But T-stat is 1.955, right? 1.955. So we reject HO. The risk level of energy stocks exceeds that of financial stocks by more than 0.25. By more than 0.25. H1 says mu1 minus mu2 is more than 0.25, right? Because of that sign, more, bigger, our confidence interval will have a lower bound. And that lower bound is x1 bar minus x2 bar minus T-crit times the standard error, which is 1.164 minus 0.738 minus 1.67 times the standard error, which is 0.09, 0.276. And so the confidence interval is 0.276 to infinity. And notice that since 0.25, did I put 0.025? This is 0.25, not 0.025. Since 0.25 is not in the confidence interval, right? This is not in this range. We reject HO, and so we reach the same conclusion as the critical value approach.